Hello everyone. In this video, we are going to talk about the BJT configurations and also its characteristics as well. So in order to understand the behavior of the BJTs in different electronic circuits, first we need to understand their configuration along with the characteristics as well. So in this video and the following a few, I will be covering the different configurations of the BJT and their characteristics. All right. We know that if we use the transistor alone, it does not do anything useful unless it is placed in a specific arrangement with a circuit, as we call it, configuration. So the configuration determines how the transistor will behave. So whether you will use it as an amplifier or a switch or other functions. So if we are going to use it in a circuit to perform a specific function, then we need to set an input and an output. But we know that the transistor has 3 terminals, and we cannot simply use it as two-port device unless we use one of them, one of its terminals as the common terminal. So, but we can use any of these terminals, emitter, base, or collector, as a common terminal. So then we will get 3 different configuration of the BJT with an input and output port. So these configuration, we can call them common base, common emitter, and a common collector. At each, every time one of the terminals is used as the common one. For the common base configuration, for input circuit and output circuit, we use emitter and base terminals as input circuit, and for the output circuit we use the collector and the base. For the common emitter, we use the base emitter for the input circuit, and output circuit collector and emitter. Each time we have here base, and base is common, over here emitter is common, and over here is the collector is as a common terminal. So that's how we name them: common base, emitter, and collector. So one might think that why we are using multiple configurations, why we have multiple configurations. So it's a really valid question. It's the reason for having multiple configuration is that each offers different input and output characteristic, like gain, the voltage gain, or the current gain, or input and output impedances, and also the phase shift as well, these making them suitable for various applications. Okay, so in this video we will be discussing about the features of the common base configurations. So in common base configuration, we apply the input between emitter and the base, as we discussed earlier, and take the output from collector and the base terminals. And to bias the transistor, we are applying a VEE and a VCC voltage supplies to the input and output circuits. So here we see the currents and potential of the transistors. So IE is the emitter current, IC is the collector current, and IB is the base current. And here also VCE, VEB, and VCB symbolize the potential values between the terminals of emitter, collector, and base. We know that IE is equal IB plus IC, and also we know that if the PN junction is forward biased, it has a 0.0 voltage dropped due to the depletion region. So, and since the emitter base is forward bias, so we can assume this as a diode, forward bias diode. So the VEB is always 0.7, around 0.7 volts for a silicon transistor. For the VCB, we cannot comment anything on this because we know that for an active region, this emitter and base terminal needs to be forward bias, and base and collector needs to be reversed bias. Since it's the reversed biased diode or PN junction, we can't know for sure what the VCB is. So from this arrangement, we can tell that VCE is equal to VEB plus VCB. So since the VEB is 0.7 volts, around 0.7 volt for the silicon transistor, and we don't know for sure what the VCB is, so we cannot know what the value of the VCE as well. We can just calculate these after proper biasing. Within this circuit arrangement, now we have an input circuit and output circuit. So therefore, we have input and output quantities. For input, we have VEB and IE as the input voltage and the input current. For the output circuit, we have VCB as the output voltage and IC as the output current. So the input characteristic so we have to understand how the transistor behaves under the biasing conditions. So we need to observe the input and output characteristics by means that it's simply input voltage, the relationship between the input and output voltages and the currents. So here we have input characteristic of a common base transistor configuration. So the input characteristic of the common base configuration is simply the relation between the input current IE and the output voltage IEB. So here we see that the emitter current is constant at 0 milliamps until around this point. So after this point, it starts to increase exponentially. So to get the correct reading, we need to keep the output voltage, which is VCB, constant, because as we see here, if you increase the VCB, for different VCB values, output voltages, we have a slightly different characteristic curve. So basically, this is the results of the early effect in transistor. We also know this as a base width modulation. So what is this early effect? We know that the collector base junction in the BJT acts as a reversed bias diode, or we have to reversely bias this for active region. So therefore, the width of the effective width of the base region is symbolized as VF over here, and the whole region is VB, WB, and the depletion region inside the base region is just the W. So when the output voltage, which is VCB, is increased, then the more electrons, because this is going to be more positive, and over here we have free electrons, and they will be attract more to this side. And also for the other one, for the base, it will be minus here and more negative. Then the holes will be attracted to the base terminal, which results in increasing this depletion region. Since the base region is slightly doped compared to the collector region, the depletion region will extend more into the base region, as we see here, than leaving just a small part of effective base region. So this affects so this region, the decrease in this region allows more electrons, because the electrons coming from the emitter part will transfer or will pass through the base very easily, since there's just a small portion left of the base. So more electrons pass through the base and reach to the collector. Now let's look at the effect of this on input current. So here we see at an input voltage around 0.76 volt. So we have around 3.8 milliamps input current for an output voltage of 1. But if we increase the output voltage to 10 and 20, we observe higher input currents, as we see here. So this, I think, basically tell us that if we want to same input current like over here, we have to apply smaller, or we can say earlier, input voltages, which I think gives the name of this effect. Let's look at the output characteristic of the common base configuration. So basically, the output characteristic describes the relationship between output current and the output voltage, VCB and IC. The characteristic is presented for the three operation regions: active region, cutoff region, and the saturation region. In active region, the output current IC is almost parallel to each other, and it's constant for a given input current IE. So when the input current is increased, the output current is naturally, it's going to increase too. And also we can see that if you increase the VCB, it doesn't really affect the output current, so which tell us that this is basically a current source. So for the saturation region, the transistor cannot amplify proper here, so the output current drops sharply here. So for the cutoff region, there is no emitter current, so which results no output current either. All right, since the transistor consists of p-n junction, then we can talk about the dynamic resistance, which refers to the change in the current in response to the change in the voltage at a specific operation region. So the dynamic range at input circuit is basically the ratio, the ratio of input voltage change and the input current change, which is delta VEB and delta IE. So we have to keep the output voltage constant, as we mentioned earlier. So this is basically the slope of the one of the slope of the input characteristic plot. So we see here the slope is really high. So if the slope is really high, then 1/over slope is going to be low compared to the output dynamic range, right, coming here. So the output dynamic range is also the ratio between the ratio of the change in output voltage and the input current. Again, so input current needs to be constant. So since this is the characteristic, this is also equal to the 1/over slope. So the slope is almost 0. So then 1/over 0 is going to be infinite number. So it's going to be really high. So we can tell over here that the input resistance, the dynamic input resistance of the common base is much more smaller than the dynamic output resistance. Okay, for the current gain, the current gain is output current over input current. Output current is IC and input current is IE. So we know that IC is equal to IE minus IB over IE. So this equals to 1 minus IB over IE. So whatever this IB over IE is, and we know that this is definitely going to be smaller than 1, because IE is much more higher than IE. So 1 minus that value is definitely going to be less than 1. So we can tell that the current gain for a common base configuration is always below 1. For the voltage gain, however, is the voltage out over voltage in. So for the voltage out, we can also demonstrate it as an IC times R out, which is input current output current times output resistance over input current times input resistance. So we know that the output of the transistor is reversed biased output circuit, because it's base and collector region that's reversed bias. So the resistance is really high. Also, we can see over here the resistance is really high. For the Rn, the resistance is really low. So also we know that this is a forward biased diode. So the results of this will be high, very high. So we confidently say that the voltage gain of the common base transistors are really high, but current gain is below 1. All right, this is all for this video. Thank you so much for watching. See you in the next videos.